Hello everyone. In this session, we will discuss about the biasing methods. So generally, what is the purpose of any biasing method? In order to make a Q point. What is Q point? Q point is stable point. Stable point. At this point only, MOSFET will act as the amplifier. Not only MOSFET. In case of BJT also, at the Q point, it will be operate as a amplifier, right? At this point only. To make the Q point and to maintain the stabilization of this Q point, we should do some biasing methods. Okay. So here, to use MOSFET as an amplifier, we should make MOSFET as proper biasing. So to use as amplifier, we need to biasing. Already we discussed about these biasing methods, biasing technique in BJT. Yes. Here we discussed about MOSFET is two types. One is the depletion MOSFET, another one is the enhancement MOSFET. So depletion MOSFET has three types of biasing methods. One is fixed biasing method, second one is self biasing method, third one is voltage divider biasing methods. So these three biasing methods are easy and you should make as assignment. So do the assignment work on these three biasing methods. These are very simple. Make it an assignment and you should prepare some notes for it. Okay. Next, we should discuss the E-biasing methods. Compare with the D MOSFET and E MOSFET. E MOSFET is very much applications compare with the D MOSFET. What is the reason? D MOSFET, in order to make it is always in off switch, it is always in on switch, and in order to make it a off switch, it required biasing. But here for E MOSFET, it is only off switch always. When we are giving the positive biasing, it will be acts as the on switch. That's why E MOSFET is very important compared with the D MOSFET. So here, before discussing the E MOSFET biasing methods, first we should discuss about the relation between input voltage and the output voltage. So look at here, this x-axis is the VGS, that means gate source voltage. It is nothing but the input voltage. And this y-axis is the VDS. This is the voltage between the drain and source. So that is nothing but the output voltage. So if you draw the graph between the input voltage and output voltage like this. So up to threshold voltage, the VDS is always the drain voltage. That means up to threshold voltage, it's like acts as a off switch. What is this drain? Biasing voltage for the drain terminal, VDD. So up to this VT voltage, it will be fixed. After the threshold voltage, if you increase the VGS, VDS is slowly decreasing and it will reach some point. Slowly decrease, it will reach some point. After that, it will maintain the linear relation. After that, it will maintain some linear relation. Okay. So at which region it is off? That means complete drain source voltage is VDD. That region is called the cutoff region. At which region both are the saturation, it will be fixed and it will be the linear region. So these are the regions, actually these are the regions, different regions. Okay. So generally in saturation region, I think this is reverse, so you should make it, this is the linear region, fixed region, and this is the saturation region. This is the saturation region. This will be interchanged, right? So first cutoff region will come, then saturation region will come. After that, it will be linear region will come. After that, it will come the saturation region. In saturation region only, it will be acts as the amplifier, right? In saturation region, by giving the less amplitude signal, we will get the more amplitude signal. Okay, you know this point. In saturation region only, this MOSFET will be acts as amplifier. MOSFET acts as amplifier. You know the amplifier which will take low amplitude signal, we will get the high amplitude signal. Okay, so that's why our intention is to biasing is required to biasing is for to operate in saturation region, to operate in saturation region. Yes, yes. So that's why in order to make in this region we should do the biasing for the MOSFET. Okay, so this is for the E MOSFET only, right? So we have three different type biasing techniques. So in E MOSFET, the first technique is the fixed biasing method. So this is the fixed biasing method. So look at here for the E MOSFET. So this is the N channel MOSFET. That's why symbol is inside. This is the drain terminal. This is the source terminal, and this is the gate terminal. So always you know that we will give the AC signal input via the input capacitance, and we will collect at the output is the output capacitance, and this is the output terminal. So these input capacitance and the output capacitance both will isolate the DC biasing voltage. Okay, this will isolate the biasing voltage. Then circuit will be isolated from this point and this point. Only this will be acting for the biasing. So to understand the any biasing technique, the most important point is always the gate current will be zero. Always the gate current must be the zero. Keep in your mind. Gate current must be zero. Yes. Here, whenever the gate current is zero, this current is Ig is zero, then automatically the biasing, this is the forward bias, so this is the biasing, this complete voltage will be stored at here VGS, because if you apply the loop equation at this loop, that means VGG, RG and GS, then what happens when IGS is 0, the drop will be at this point also 0 because current is 0. Then I will write one thing, that is voltage across gate and source terminal is nothing but the VGG voltage. And generally drain current, you know that the formula for the drain current ID equal K into VGS minus VT whole square. VGS minus VT whole square. Here ID is the drain current, nothing but the output current. VGS is the input voltage. So this is not input voltage, this is the gate and source voltage. And VT is the threshold minus whole square. Here already I told you the K depends on the device parameters, but we can extend the ID is like this. The ID is, the total formula is 1 by 2 mu n into COX W by L into VGS minus VT whole square. So here this is of, what is mu n here? Mu n is mobility of electrons. Generally this is the mobility of electrons. And what is COX? COX is nothing but oxide capacitance. COX is oxide capacitance. So what is W? W is width of the channel. So we have channel here that represents width of the channel, and L, you know the length of the channel, and you know remaining things. Okay, so simply we will say that, so you should maintain this current. So generally if you draw the relation between the output voltage and this current, we will get the two things. we will get the two things. Those are like this. So if you draw the characteristics is, if you take the characteristics, this is the drain to source voltage and this is the drain current. So if you draw this, you will get like this. One thing, and the second thing, the third thing. So by depends on the VGS. So this is the VDS and ID, and next is the, so if you draw the relation, the Q point and biasing point is, you will get like this. You will get this load line. So this is VDC represent VDD and the current represents VDD by RD and the 0. So for example, in order to take this, so we will get the two things. This is, one is the VDS is the point, next one is the ID is the current. So in order to, if you take any VGS value, this is the different VGS values. If you take, if I want to operate input voltage VGS at this point, then you in order to work as an amplifier, you should operate at this point, because it will satisfy this curve. It will satisfy this curve. Otherwise, it is not possible. Okay. So generally, this is the fixed biasing technique. This fixed biasing technique have some disadvantages. Those are, the first point is, it is not efficient method, because here this biasing method depends on the not efficient. The reason is, it depends on the mu n. Mu n means mu n and the COX. Mu n and the COX. Mu n means it's a temperature coefficient, and it will depend on the COX and L. These are the terms. It will, drain current will depends on these terms. So these are generally vary from device to device. Okay, and so these are a variation term. Due to this variation of the terms, the Q point will be changed. So that's why this is not a efficient method, because depends on these techniques. Okay, and so these are the disadvantages. These disadvantages are eliminated by the next methods. So coming methods. Okay, so the next method is the voltage divider biasing method. This is the voltage divider biasing method. Look at here. So same circuit, drain, gate, source. This is the N channel type, and we are giving the input through a input capacitance, and we are taking the output from the output capacitance. And look at here. So the previous, so always you should give the biasing through a resistance, that is the RD resistance, and source have the resistance RS. If you observe here, then we should connect two resistance. One is the R1 resistance and the another one is the R2 resistance. You should connect the two resistance. These two resistance will be useful for to divide the biasing. That's why it name it as a voltage divider biasing. So keep your mind, always the gate voltage is 0. Okay. Yeah. Generally, you know that whenever analysis in the DC biasing, this capacitance will isolate the input voltage, and this capacitance isolates the output voltage. Okay. Next, so how to find this voltage VG, gate voltage? So I can write like this. This is the complete drop, and this is the current. We need to find out the VG. VG means drop across this R2. So I will write here, the VG is, equaled, so I will write current drop is VDD, and this is the flowing current VDD by R1 plus R2 into this resistance. This resistance is the R2. This is the voltage across the gate, first point. And next, you will look at the apply the just input loop for this voltage. input loop for this voltage. So how can we write? So I will write the input loop. Input loop means this point to this point. How can we write? So this is the VG minus VGS minus ID RS. Is it okay? So the current flowing through this is the drain current, that is ID, you know that. Yes, and the voltage in this loop is VG is the point, and this voltage is VG, and this is the VGS minus ID into RS, because the current will flow in this is ID. Okay, ID RS. From this I will write the VGS equal the VG minus ID RS. So I am getting the input voltage is VGS is ID RS. Okay, take it as a first equation, keep it as a first equation. So input analysis will be completed. Next, go for the output analysis. So apply KVL, output loop, apply KVL in outer loop. What is the output loop? From VDD to this point is the output loop. Now I will write like this. So I will write this is the voltage VDD minus this drop IDRD, and this drop VDS, and this drop IDRS equal to 0. This is the outer loop. From this I need to find out the drop across VDS equal VDD minus IDRD minus IDRS. From this I will write VDS equal to VDD minus, if you common the ID, that is RD plus RS. Okay, so we have two equations. First equation is the input voltage, you will get the VGS input voltage, and second equation is the output voltage, that is the VDS, that is VDD minus ID RD plus D. Okay, so by using this voltage divider biasing, so what happened? So we will analyze like this. So for example, if you increase, if the drain current, you are increasing the drain current, then what about VGS? Look at here, VGS, I am increasing ID. What happened? VGS will be decreases. Okay, and whenever VGS decreases, again you know the ID current value, ID is K into VGS minus VT whole square. When VGS is decreases, what about ID? ID value also decreases. So for example, if the drain current value is not in our control, generally ID is increases, but by using this voltage divider biasing, what happened? By using this voltage divider biasing, drain current will be decreased. So we can write one point, it prevents drain current increase. It prevents the drain current increase. Okay, so that's why this voltage divider biasing is very much useful, very much important and the useful. Okay, and so here by adding the source resistance, so we have the source here, it has some resistances, the parameters also minimized, parameter variation also minimized by using this parameter variation also minimized. Okay, so that means properly, if the drain current is in our control, it automatically controls the drain current. Okay, so that's why this voltage divider bias is very important. So in case of BJT also we have voltage divider biasing, that time voltage divider biasing also very much applicable. Okay, so with this voltage divider biasing we have some more techniques. The next technique is the MOSFET biasing with the two supply voltages. Look at here. So two supply voltages, we are giving VDD is positive side and VSS is the negative side, and we have the input and we will collect the output from here, and here we have RG here. So gate resistance we are providing gate resistance here. So this is also a good technique. This is also a good technique. What is the application of this RG? RG provides high input impedance. It will provide the high input impedance. Okay, high input impedance. It is also very good. We have the very good applications by this biasing technique. Right. Next technique, drain feedback biasing technique. So look at here. Same thing. So drain has resistance. Here source doesn't have any resistance. From the drain only we are connecting a resistor RG. That's why it is called the drain feedback. From drain terminal we are connecting the feedback resistance. That's why it is called the drain feedback terminal. Yes. So same input capacitance as well as output capacitance. So this is the output. So we will analyze it. So initially you know that for any MOSFET the gate current is the 0. So here I will write initially the gate current is the 0. So whenever the gate current is 0, there is no current flowing into this. There is no current flowing from this terminal. So leave this. It is isolated. This doesn't have any relation. Leave this input and output. That's why the voltage across this point VG and the voltage across this point both are shorted, because whenever current is there is no current means there is no use of the resistor. Resistor is acts as a short circuit. That's why I will write the drain voltage equal to the gate voltage. Okay. So can I elaborate this? This VDS voltage and VGS voltage both are same. So I will write drain source voltage and the gate source voltage both are same. That is, from this we will remove this drop. VDS is nothing but, I will write the VDS value. What is the voltage? This voltage minus this drop, we will get this voltage. So I will write VDS or VGS is like this: VDD minus ID RD. Okay. So I will write like that here. Again, this is the one equation, so no problem at all. So now this is the equation 1. Take it as a equation 1. You know the drain current ID. ID is like this: K into VGS minus VT whole square. Okay, you know this voltage. So I will write again the ID. ID is like this. So K into mu n COX. So W by L VGS minus VT whole square. Okay. So same concept here. If the drain current is increases, what happen? What about VGS? Drain current is increases. VGS, what about VGS value? Here VGS is the decreases. Same thing. Whenever the VGS decreases, so here the VGS is decreases, then automatically ID value decreases. So ID is increases, but ID value is decreases. So this way we will stabilize the circuit and operate point. Stabilizing the circuit and the Q point. So circuit will be stabilized and the Q point. Okay. So this drain feedback biasing method also a good technique like this, right? Okay. So finally, what is the thing means, you need to note this point here. The note is like this. Here the note is simple. What we tell, both techniques, voltage divider biasing technique and the drain feedback biasing technique, okay, try to stabilize the operating point. It's always try to, these two are stabilize the operating points and effective methods. Stabilize the Q point. Okay, yes. But still we have variation in, but still some variation in Q point. Some variation in Q point. Some we have some variation. It will be stabilized by the below methods. It will be stabilized by some below method. So next method will be more efficient than this voltage divider bias and drain feedback biasing techniques. The next method is constant current biasing. The next method is the constant current biasing. Here, look at here. So this is also same symbol IGBT. Don't confuse here. So this is also the same symbol. Sometimes he will give like this, no problem. So here, look at here, V0 and V. Remove the V0 and V0. Just look at VDD have resistance RD and we have the constant current. So whenever you put the same constant current, then any variation in the circuit parameters, there is no change in the output current. Output current should be fixed. Output current should be fixed. And if you observe here, a drain terminal as well as the source terminal, we have drain terminal have positive biasing and source terminal have the negative biasing. Okay, this is the current and this is the gate terminal. This is the gate terminal and the current. Okay, yeah. So what is this meaning when you are putting the same constant current? What is this meaning? The output current or the drain current, drain and output current is constant. Is constant means what we told operating point is stabilized. We can tell that operating point is stabilized. So the stabilization is done here. So any variation in the circuit that will not affect here. And so this and this constant current source, the constant current source nothing but this is the constant current source is generated by current mirror circuit. So we discussed the current mirror circuit in BJT is generated by current mirror circuit. Current mirror circuit, okay. So this method, this constant current biasing method is very robust method, very robust method, very toughest method, and very robust method than other methods. Okay, so this method is simple by putting a constant current, but it will be given by the current mirror circuit. Okay, so these are the biasing techniques of the E MOSFET. So you should write the assignment on the D MOSFET biasing techniques. Okay, yeah. So I hope all of you understand these biasing techniques, and most applicable method is constant current biasing method. Okay, thank you.